This is probably my favorite part of this summit, which is now in its third edition. We can say it's an annual thing now once you hit the third one. I think that's the rule.
Absolutely.
So as you know from looking at the program, there are two competitions. One of them is the startup competition. The one that's about to start right now is the Entrepreneurial Computer Vision Competition. Now, it shares some DNA with the startup competition, but there are some important differences. With the startup competition, we're looking at company pitches that are entire startups, business plan, product idea, team, all those parts. In the Entrepreneurial Computer Vision Competition, the ECVC as we call it, what we're focusing on is the computer vision piece. So there may not be an entire company built around this, and this is important for the judges to know. There isn't an entire startup necessarily built around it. It's a computer vision or machine learning or computational photography piece around which a compelling startup idea could be formed. Okay, so we're focusing on that computer vision part. It may be presented by a graduate student at a top university. It could be an experienced engineer who had been at a large company and left to do a little startup. So I just want to emphasize that little difference from the startup competitions, which you'll be seeing later. And we have an incredible lineup of judges here. And they will be judging each pitch, these short pitches. They're 4 minutes each with a little bit of Q&A afterwards, on the basis of criteria that are similar to the startup competition, but really focus on the potential of the business idea. Okay?
Fantastic. Thanks, Serge. And just to elaborate, instead of the questions in the startup competition being, what's your business model? Does that make sense? This is it commercially viable? Where do you think it would make sense? How could it impact humanity? And also I'm going to reiterate that we always get comments of, wow, you've got a lot of judges. Why? Obviously, the more data we have about people's feedback, the better. Also, we would love to co-invest and find companies to do together. Positive, and have more people here interacting. So it's kind of a win-win for all. That's why we have many phenomenal judges that you can't see anymore because my bald spot is up there. On that, we're going to kick it away. Just so everybody knows, the judges do 1 to 5 ratings on opportunity, commercial viability, traction, technology, team. The winners get 5,000 credits for Amazon. If somebody wants to invest in them, that's even better. So on the first note, I want to bring up MD.ai from Cornell. Leon, come on up here. You got your mic?
I don't.
It's right here. And there's your clicker. And just the clicker goes out to there. And go for it.
All right. Thank you, Evan. So I'm Leon, and I'm here to tell you about MD.ai. Our mission is to save lives with AI.
Okay, let's reiterate that. So we go here, click once, and you go.
There we go.
Okay.
So my co-founder George and I, we're both doctors with deep learning experience. We both have engineering backgrounds, and George is a practicing academic radiologist with leadership roles at Cornell and in national radiology organizations. Come on. So George and I became acutely aware of a growing problem. There's a shortage of radiologists everywhere. These are the specialist doctors who read your chest x-rays, CTs, MRIs, and ultrasounds. Now, the volume of medical imaging is growing rapidly, but there are not enough doctors to read them all. That's an incredible number of potential life-saving diagnoses that are missed. So here in New York, we're fortunate to have about 1,000 radiologists. But consider Mozambique, population 26 million, only has 3 certified radiologists in the entire country. So the World Health Organization estimates that over half the world does not have adequate access to radiology. So with MD.ai, we are tackling the problem by applying deep learning for the most common exam performed, the chest x-ray. Now, chest x-rays can reveal diseases such as tuberculosis or lung cancer. Now, 80% are actually normal, and only 20% are abnormal. Unfortunately, doctors are still spending precious time on the normal exams. So we want to change that. We want to make radiologists 10 times faster and better at identifying the abnormalities. So reduce costs, increase efficiency, and results in better patient care. So we've implemented our own version of deep residual networks with stochastic depth, which uses layer-wise dropout during training time. And this allows us to train hundreds of thousands of network layers faster than was previously possible. And that can translate to increased performance as well. So using our implementation, we developed a model to simultaneously classify chest x-rays as normal or abnormal, as well as to perform anatomic segmentation, for example, of the lungs.
4 minutes per each speaker.
And that allows us to automatically localize any potential abnormality. Now, as you can see, we've achieved some amazing early results with over 95% accuracy. So I can tell you from experience that algorithms alone are not enough. We need better communication too. So that's why we're building web and mobile apps for everybody involved, from the doctors to the patients. Now, not only are we building algorithms, but we're treating patients too. So we started about 2 months ago, and already we've developed a large partnership with a large radiology practice for data, and we're planning to launch a pilot by the end of the year. Now, there are a lot of people trying to get machine learning into the hands of doctors, but what really sets us apart, George, my co-founder, and I, we're both MDs with the deep machine learning skills to actually make it happen. So now I want you to imagine an AI-driven healthcare future. It's a future where costs can be reduced. It's a future where more patients can be served than was ever possible before. Lives will be saved. And we want to help build that future with MD.ai. Thanks a lot.
All right, well done, Leon. We'll put the clock back to 2 minutes for questions. Who wants to kick it off? Howard, you got a mic? There's a mic right in front of you.
So one of the questions is going to be how big the training set, how much training data do you have for this? Because
exactly.
you got to get a lot of training data.
Yeah, that's a key piece.
We need a mic on over here.
So, is this on? So the results I showed you, so that was on tuberculosis, a special, a specific disease. And with that, we had about a couple thousand X-rays, and the results were on a 10% validation set. I know you made the comment earlier that we probably need millions of X-rays for this to work, but I'm confident that we can get pretty close with 10 to 100,000.
Next question. Yes.
Hello. Yeah. As far as I understand, in medical imaging, if you make an error, you miss a diagnosis, it's pretty costly. So you're saying with 95% accuracy, is it good enough to go to the market?
Right. So I just want to reiterate again that making the diagnosis is only a small piece of the larger. The entire. You got to consider the entire healthcare process, right? So we initially focus on just identifying if an X-ray is normal or abnormal, and even that is tremendous. Amount of information that doctors can use. So, your wait time can be reduced from hours waiting for radiologists to read your X-ray, to almost instantaneously, right? So, finding those key pieces that you can really attack in a meaningful way will get you a long ways.
It's on.
So you mentioned communication. Can you say more about that? Like communicating with both your patients, I guess, and with experts? I don't know who would give you the
Right.
extra 5%.
So everybody involved. Patients. I think everybody in this room probably wants ownership of our medical data. We want to be in the loop all the time, right? But for doctors and radiologists who we work with, there has to be really clear communication, as to what everybody is thinking about. So a radiologist, it's not enough to just see something, write a report, and send it out. Really, the doctors taking care of the patient want to hear from the radiologists sort of like their thought process as well. And unfortunately, in our current healthcare environment, that doesn't necessarily always turn out, it doesn't always bear out.
Anybody have one last question? Go for it.
So there's an inertia. There's inertia with trying to get automated methods through to be accepted in the community at large.
Right.
Do you have a plan to get over that?
Oh yeah, absolutely. So we are working with radiologists initially. So not a single image that gets read by our system gets passed along without a certified radiologist looking at it as well. That's a key piece. I think there's a big question in this field. How are you going to label and annotate all these images, which requires specialized training to do so, right? And if we can build that key piece in there, we can get very far, further than our competition, I think.
Okay, round of applause. Thank you, Leon.
Thanks a lot.
Next up, we have DeepALE coming in from Oxford. We have Kyle. What I love is we've got Cornell, Oxford, Carnegie Mellon, Cornell, diverse audience. Take it away, Kyle.
Hello, can you hear me? Yeah. I'm going. Okay, thanks. So I'm going to present the project we are doing. It's called DeepALE, and it stands for Autonomous Labeling Environment. And our goal is to find a solutions to have holistic image understanding with semantic image segmentations. So this is our team members. We are all from Oxford, and our professor Phil Toles has 25 years experience in research, and all the other members, we all have a lot of experience in research as well. So what is semantic segmentations, you may ask? So the goal of semantic segmentation is to recognize and also delineate the objects from the images. As you may see from these visualizations of our systems, we are trying to figure out which pixels belongs to person and which pixels belongs to the bicycles. One of the possible question you may ask is why we need semantic segmentations, why we need pixelized localizations techniques. So one project in Oxford we are trying to develop is to develop smart glasses for partially sighted people. So our semantic segmentation technologies could help partially sighted peoples by highlighting the important objects in front of the wearers, but also telling the wearers what's going on in front of them. So our solutions to this problem is to use deep learnings to understand the meaning of pixels. So in contrast to the convolutional neural networks that does classifications, our works basically allows pixel-wise labelings. So given the images, we will not only tell you which pixels belongs to what object, but also we will have much better boundaries to highlight the objects. This is the works I'm working on in my ICV last year submissions. So compared to the other competitors, so our ingredients, which is called a CRF iron, it helps the CNNs to achieve better semantic segmentations compared to the other competitors. And if you compare our result to the human label annotations, you will see that the output of the neural networks we develop is even better than the human annotations. So how this is going to be useful for the arbitrary images? And so we develop a website which allows the users to upload whatever images they want. And one of my favorite images from Reddit, so the users upload a cat. So our systems can not only recognize the cats in the images, but also to tell which pixels belongs to cats, no matter where the cats are and what they look like. Okay, so the potential impact of our project, it basically empowers the machines to understand the world around us. So here's the photos from the, basically based on the result from our systems for the cityscape dataset. As you can see, with the semantic segmentations, the machines, the autonomous beer, they not only basically tell whether there's a riders in front of them, but also knows which locations of those objects. So this basically enables the vehicles to basically can pass the hazard perception test, if I may say. So thank you very much. If you want, you can actually try our demos by uploading the photos. So thank you very much.
Okay, well done. All right, judges, who wants to start? In the back, if you pass it, do you have a mic? We pass the mic back there, Ramesh. Okay.
How do you tell your system what the objects are? Because in the last picture, you were labeling vegetation, but in the first picture, vegetation was completely ignored.
So that's basically, so the systems actually, so we were showing the result is actually, we first have to train deep neural network models on a labeled data set. Well, the first kind of images show you where the person and where's the bicycle. Basically, that's based on the annotations in a data set. It's called a Pascal VOC data set. And it's also partially trained on the Microsoft Cocoa data set. And so the autonomous vehicles, that images shows you, they basically train on a different data set. It's called a cityscape data set, while they have the annotations for which part of the images belongs to person and which part belongs to the road.
Larry?
So there's a lot of image segmentation algorithms out there, and
Yes.
it seems like your differentiator is having slightly better segmentations.
Yes.
Can you give an example of an application where having slightly better segmentations is going to have a big impact?
Okay, so that's really good question. So basically, our unique part of this work is we have the special component. It's called a conditional random field as a recurrent neural networks. So that specialized the components enables the segmentation system to have much better sharp boundaries. And in applications, for example, like photo editing, you really need the result, the segmentation result, to have really high quality boundaries. That's where the our works will be used for, and similar to the other applications as well.
Hey, have you guys crunched the numbers to figure out what it would take for you to kind of database everything in the world, so I can go to my backyard, point to a tree, and it would tell me what it is?
Okay, so that's a good question. So our current systems basically is still supervised learning systems. So we need to, first we need to get the data, label the data, and then we train the models, and then we deploy the models. So right now it roughly takes maybe 1 week to 2 weeks, depends on like how many people and how many machines you have. But I think to actually accomplish the task you set up is to labeling the whole world. We actually having sort of systems whether we allow the users to actually interactive label the systems, which we're collaborating with Microsoft. It's called a semantic pen to labeling the world. So of course, there's a lot of technical problems around there, but I think it could eventually be solved.
Okay, last question, real quickly.
Yeah. So I could see a lot of applications in fashion, where you want to like split the human body into like shirt and pants. But my question is, how much training data would you require? Say if I give you a simple problem like shirt and pants, how many images are good enough? How many labels are good enough?
Okay, so so in Pascal VOC we have roughly so around 10,000 images that's being annotated, And of course, they are actually annotated in different qualities. So that's actually, with that amount of images, we can now get 70% intersection over union scores. Let's give you rough ideas how good it will be. So the more data you supply, the better result you would expect.
Okay, thank you very much, Kyle. Round of applause, folks. Next up, we have Love and Vision. Divyaa from Carnegie Mellon, come on up. The button is right there on the right, and you're going to point it that way.
Hi. So this is what we're calling our project. I'm Divyaa, and there's a guy at the back, and he's my teammate. He's Harsha. We're both graduate students from Carnegie Mellon. So today the question we're trying to answer is whether we can verify the existence of relationships between people. What I mean by that is, suppose we had images of two people, right, just their faces. Can we look at them and say if there is a relationship between them? Can we say, for instance, whether they're mother-daughter or father-son? Or can we even say if they're partners, for like husband and wife? An initial step towards this, we're trying to tackle the problem of kinship relations, mostly because it's easier, because, you know, as humans, you can tell if it's a parent and a child, right? So suppose we had pictures of Barack and Malia, right? And we have no other information about them. We don't know them. Can we just look at these pictures and say that, yeah, there is a relationship between them. In fact, they're actually father and daughter. A more lofty idea is to apply this concept to couples. Now, we know that couples don't look like each other, partners don't look like each other. It's highly unlikely. But given that a person looks the way they do, what can we say about their partner? Can we say that Brad likes Angelina and he's going to like anybody else who looks like Angelina? Can we extrapolate it that far? That's the question we're actually trying to answer. Yes. So technically, how we're trying to do this is by using Siamese networks. We're trying to teach a parallel deep network to learn features from matched and unmatched pairs. This is the architecture of our network. So we have two convolutional neural networks running parallel to each other that share weights. And the input to each of these networks is an image from the pair. In this example, you see Jada Pinkett is the input to one and Will Smith is the input to another. And the network learns a loss function and then tells you whether this is indeed a matched pair or if it's not. Yes. So the main pitfall of, one of our biggest challenges is that we're low on fuel. And we know that fuel is data that powers a neural network, and we have very insufficient amounts of it. Where we're trying to do the kinship relationships, we had about 2,000 pairs of images. And when we were trying to extrapolate this to the couple scenario, we realized that there is no data set that is in existence out there, so we had to build our own. And right now, while it's being built, it still stands at 1,000 pairs of images. Some of the results here are based on the kinship relations. So the table on the left, that's the left, yes. The table on the left shows you results of our network as compared to some human experiments that were carried out on different relationships. As you can see, our network seems to be performing a little better than the humans. The graph on the right is showing the projected deep feature space. Here, the idea of the network is it reduces the distance between two images that form the part of a pair, and while increasing the distance across pairs. So, for instance, a mother is closest to her son and further away from every other child than she is from her son. A potential application of this would be improved recommendations in matchmaking applications and websites. This, I believe, would boost user experience because now you'll just have to enter one image into this application, say, one of your images, and it should ideally be able to give you suitable matches because it has learned some rules about how people pick partners, and it's not going to ask you any more questions. No swipe rights, no questions about what your likes and dislikes are. It should ideally be able to tell you what kind of people you're going to match likely best with. Thank you.
All right, applause. Thank you very much. Hey, Larry, do you know a data set that they might be able to use? At Facebook, for anybody that doesn't realize who I'm pointing to. Yeah, Erik.
All right. I have a question on how much does your score vary between pairs of images. So if you have 20 images of Brad, 20 images of Angelina, how much does the score vary on all of those combinations?
We actually tried that, and so you see the graph that I showed you earlier. I think I can go back. Yeah, that graph. So when we tried it with the same couple, right, they are very close to each other. They form like a sort of cluster. So different images of the same couple, those points are closer to each other than they are to other couples that are not there. Especially, and if it's the same image, they're like overlapping. They're the same point. Did you understand what that means?
Yeah, no, I meant more in the validation when you're doing your results. If you're looking at unknown pairs,
right,
how much does it vary based on the actual picture of that? So if you have 20 instances of one person, are those 20 scores?
Are you saying if it picks out
close, or are they spread out?
They're close. They're pretty close. They're clustered around the same region. So graphically speaking, they're pretty close.
Okay, and how much training data do you think you need to make this really work? With
we have
Facebook
very
and other
insufficient
places.
right now. I believe that right now it's a mixture of we have people from Hollywood and Indian people and Korean celebrities is what we have right now. We're trying to add in as much of a mixture as possible, but we think that the more of a mixture we add, the more it's likely to just classify based on races, because that's the first thing it's probably going to pick out. But we think that if we could have a large enough data set with, say, just like Hollywood, maybe like Caucasians, right? So it's likely to be able to pick out more nuances within it and not just be like a racial classifier as it would be if we mixed everything together. So we think if you make it exclusive for one kind of race, then we'll actually get the network to learn something from that.
Kristen.
So do you think you could modify your algorithms to make it a prediction network where two people could predict what their potential children would look like? And do you think that would increase the commercial viability?
Prediction is not something that we've explored, but what we wanted to try was we give it an image of one person, and we give it images of like one partner, right, to one end of the network, and to the other network you give it like 50 random people, and then it could tell us which are the closest out of these that it could match. Prediction is something that we haven't thought about.
All right, good question. Last question, Howard.
So, I mean, at Carnegie Mellon, you have thousands of students who can give you family pictures. Couldn't you use that as a training set on their kinship?
Yes, actually, that is a very good idea.
Yes, Howard.
We did this in the last couple of weeks of our semester. So we put together what we got from the internet. And we weren't sure of how copyright worked. And it's not something we wanted to get into at that time, which is why we just pulled out images from Google celebrity search. Safest because it's always out there.
Go find Howard afterward. He might have other suggestions. Thank you, judges. Okay, one more. Thank you very much. Bringing up our last competitor. And then we go to a fireside chat with Bijan. Sean Bell, GrokStyle from Cornell. Take it away.
Hello. I'm going to talk about GrokStyle. We do visual understanding for interior design. If you're curious, Grok means to totally and completely understand something. It's from science fiction. So GrokStyle is based on my last 5 years of my PhD research at Cornell University. And Kavita and I co-founded the company, and Kathleen joined us early on as an engineer. And so as experts in both crowdsourcing and deep learning, we have the ability to both build the best algorithm and the best data set to train it on to really succeed. So today there are sites like House, Porch, Pinterest, and recently Contour that have large communities of people who are interested in interior design. And so there are people here who are spending hours browsing interesting pictures and products and showrooms looking to get inspired. The problem is that we're just drowning in these images. You can't get inspired if you can't find the images you like. So if you look on house.com, people can leave comments on photos. And they leave all kinds of the comments like, what is this? Who's the manufacturer? What's the color? There's a clear need here. People want answers to visual questions. And this is where we come in. We want to build a system that can automatically look at any product and tell you, what is it? Where can you buy it? How much does it cost? So to solve this, we train in embedding. The embedding works by taking a new image that it hasn't seen before, projecting it into the embedding, and then retrieving the nearest neighbor. So here in this example, we just found the Helmer ring hanging light. But we can use it in other ways. We can take a product, we can project it back into the embedding, and then look at what training images are nearby. And so now we can start to detect objects and scenes and find where have people and where have designers used this. So to gather the training data, which we use to learn our embedding, we put it on Amazon Mechanical Turk, and we set up an interface where on the left you have the product that you see in the store, and on the right you see the item in context in the scene, and a worker is cropping it out. So giving our data, we set up a pipeline like this. We collect our image pairs from Mechanical Turk, and we train a deep neural network. We take the parameters, and then we download an image database, we pass it through a deep neural network, and then we look at where every image lands in the embedding. So this forms like our lookup table for visual search. And here's a visualization. This embedding is massive. It has 3 million products we looked at. And so you can see that it's generally organized by object category and by visual similarity within each object. So the deep neural network knows exactly where to place everything in embedding, and that's what it makes it work. So here's a picture I took. So yesterday, as I was coming in, I saw this in the lobby, and this chair caught my eye. So I thought, oh, this will be great for a demo. So here a user indicates the region of interest. Our deep neural network projects it in the embedding, and here on the top left, you can see that the correct product was exactly next to it in the embedding. Nearby, there's visually similar products. We can project it back into the embedding, and now we're looking at scenes where designers have used this product. And so you can use it to get inspired for your next project. We quantitatively evaluated our system on a holdout test set of 10,000 image pairs. We evaluated several variations of a neural network architecture called a Siamese net, and they all do really well. We compared against 2 baselines commonly used in past work, one where we train on object categories, and another where we use a pre-trained neural network. Compared to the baselines commonly used, we got more than a 2x improvement. So what's next? We want to be able to take any photo from anywhere, any photo you find online, any photo you take with your cell phone, and we want to be able to tell you all the products in there, how much they cost, where can you buy them. We're currently working with IKEA to make this happen for their products. We want to be able to allow you to take any product and see how have designers used this, how can I get inspired, what products go well with it, how can I use this, and so you can use this to understand what goes well together. And then finally, by looking at where have our system found these products in real-world images, you can start to understand the aggregate of what is the worldwide use of this, what's the visual analytics, how much is each country using this. Thank you very much.
All right, who wants to go first? Judges, meaning.
So Pinterest has something like this, right, where you can drag and it gives you everything. So is it, I mean, have you compared with them or how are you different from them?
We have compared with them. We've talked to them. So I've talked to their engineer. I believe our system is significantly more accurate, and it would be really great if we can get them to use our system, because I think they'll get much better visual searches.
Question, Beth. Oh, yeah, all the judges are speaking. Excellent.
Hi. So you said IKEA. You're
Yes.
working with IKEA. How is IKEA going to use this?
So IKEA has several use cases. One of them internally is actually they're so big and they have so many employees that their own people can't find all the photos. And so just within internal use, they want to avoid redesigning scenes. This can form like a test case where if it's sufficient for recognizing products, then they want to turn it around and show it to consumers. And so consumers browsing the site can understand and search within the IKEA catalog. It's just too big. There's too many photos.
Can you talk about some of the attributes of interior design specifically that made you choose that over other things like, you know, apparel or whatever?
Yeah, sure. So there's lots of domains you could apply this to. The reason why we choose interior design is because it's sort of the optimal balance between something that works really well for computer vision. These are rigid objects. They don't deform. So although clothing has lots of applications, it's much more accurate if you just pick objects that are easier to recognize. And so we want to move into apparel in the future, but that's why we started out with design.
How long does this take to run a search?
At test time, it takes about 20 milliseconds to project in the embedding, about 20 milliseconds to look it up. So overall, we can get a response back to the user in about 100 milliseconds, although probably we can get it down to 50. So very fast, instant.
If successful, how far do you expect it to scale? And do you see any problems with scaling?
Scale in terms of number of images, or like if we number of images. So right now we can do a visual search across. So those numbers I gave are for 3 million products. And I think that's many, like people don't want 3 million products. They want really good products. They want a subset of that. And so I don't think actually scaling to larger numbers of products is going to be that much of a challenge. We're also looking into partitioning the space by category. And so if you predict what category, then you can search over a smaller number of items. So there are many ways to accelerate it, but I actually think the scaling challenge will be more on the business side and less on the photo side.
Anybody else? Any other questions? Round of applause. Thank you very much to all of our competitors.